Good morning, dear students. Now we are in session 6 of module 1 of the subject Computer Organization and Architecture. So in the previous session, we discussed about memory assignment, memory sequencing, etc. So in this session, we'll look into how do we execute the instructions and what order the programs are getting stored in the memory and how branching takes place and related to condition codes also we'll just check. So previously, when we discussed 3 address, 2 address, and 1 address instructions formats, so we have written small programs to execute this kind of tasks like adding 2 numbers and storing it in C or something like that, right? So the memory map for this kind of a structure is shown like this. So as we can see here, so I'm just trying to highlight again. So your program is also stored in memory. The data is also stored in memory. So we should again remember always that programs and data always stored in memory and in sequential order. So that means processor will try to take the first instruction, execute that, then come to the second instruction. So one by one, it tries to execute that. That is called as straight line sequencing. Okay. So we assume that memory is byte addressable. That means one location stores 1 byte of data and the word length is 32 bits. That means one information occupies 4 locations. And we assume that processor has many registers to operate. And we can give one memory operand per instruction and full memory address can be specified. Now we will try to use a 2 address instruction format and see how these instructions and data can be stored in memory. Okay. Since we are assuming 32-bit length, that means 4 bytes long, successive instructions would be storing at I plus 4, I plus 8, etc. So this is what is shown here, I, X, whatever the address namings you can use. So the first will be at I, next will be at I plus 4. The other instruction would be at the address I plus 8. That means we assume that instruction and data both are of 32 bits in length. Okay. So how actually this straight line sequencing works? Okay. A simple program for C equal to A plus B and the memory map is shown in this diagram. So what happens is whenever the CPU wants to execute the instruction, the address of the first instruction is to be loaded in a special register known as program counter. So this we discussed in earlier sessions, program counter, MAR, MDR, all those registers, right? So once the program counter is loaded with this address, it tries to fetch this instruction code, and then that instruction is moved into IR, as we know in the CPU, the instruction register. Then it gets decoded there and the operation is going to take place. Okay. Now, after taking the first instruction, automatically PC is pointing to the next instruction. So PT is auto updated. So it points to the next instruction in sequence. Okay. So this is called straight line sequencing. And during the execution of each of these instructions, PC is incremented by 4 to point to the next correct instruction. Okay, that is how the sequencing works. This is good if all the instructions are executed one by one and we are not making any changes in the sequential execution pattern. Okay, but there are so many cases where we need to take certain decisions. For example, if temperature is more than say 30 degrees centigrade, we have to switch on the AC. Or if it is less than 10 degrees centigrade, we have to switch on the heater. So in many practical situations, we need to monitor some parameters, write a program in such a way that we have to take some decisions like that. In that case, the program structure and the sequencing will alter. Okay. Another example is something like adding a set of numbers. Okay. Suppose I want to add some 10 numbers. Earlier, we have shown an example of C equal to A plus B. Just 2 numbers we were adding. Let us say I want to add some N numbers now, 10 numbers, 20 numbers like that. Or a simple example is like I want to know the total score of all the students in tests or something like that. Then I have to add all the marks, right, of all the subjects to know the total score. So then this will be a real complex operation if I try to do this kind of a instruction, in fact, 2 address instruction sequence. So I'll take the first number, add it, then I'll take the second number, add it, I will take the third number and add it. So that means the same instruction, add, etc., is repeated so many times, because we have to add all 20 numbers or 30 numbers or something like that. So finally, of course, the sum, the result is stored in a location known as sum. Suppose this is the result location. So these are all the numbers for you. So this is the program area of the memory. So we just, okay. So this is what we were doing. This is the program area of the memory. Okay. And this is the data area of the memory. Now you can see here, writing separate add instructions to perform the same addition operation is little inefficient, of course, time consuming, and the program looks so unstructured. You can see here, that means same instruction is repeated so many times. Just have to take the next number, that's it. No other operation is being done over. So I'm not doing any new operations. I'm just taking a new data, that's all. So that means we can repeat this operation many times, right? Because same operation is done, except that the data is getting changed. So there are certain situations wherein I will do this kind of operation that is repetitively doing the same operation, which we call it as a program loop. So I have given you two situations now where straight line sequencing is not possible. One situation is what I said, decision making. So based on a particular data or a parameter value, I would like to see whether I need to execute some set of instructions or other set of instructions, like switching on an AC or switching on a heater. Another example is like if I'm doing something up, some operations repeatedly. For example, I want to find factorial of a number. I have to multiply it so many times, n multiplied by n minus 1 multiplied by n minus 2. So writing these kind of statements line by line is really time consuming and unstructured, doesn't give you a best possible way of efficient program writing. So these kinds of structures where repetitive task is done is known as a program loop. Okay. So in this kind of situation, we can alter the sequence of execution. Okay. That is what we call it as branching. Okay. So one example I showed, suppose if temperature is greater than 30, I'm just, suppose if you try to write a flowchart, maybe in C programming, you studied this. So you had two options, yes or no. This is one kind of a branching. Branching means decision making, as simple as that. So if temperature is greater than 30, do some action. If not, do something else. If else structure, if you studied if else kind of a thing in C programming, this is almost like that only, right? This is one kind of a situation I'm going to illustrate here. Another situation what I there in this particular example is looping. Looping means doing the same task repetitively. Again, this also you studied something called as a for loop in your C program, that you write, suppose you want to add an array of numbers, then you use a for loop, right? So that means you know how many times you need to execute this. So many times the action is being repeated. That means it won't go to the next part of the program unless it completes this only. So that means it returns to the beginning of the program itself until it completes. So this is kind of a branching or changing the straight line sequencing, changing the execution sequence from straight line to something else. Okay, this is called as branching. Okay, so the instruction in this case particularly, what is that? We are trying to add n numbers, right? So when I'm trying to add n numbers, instead of writing add num1, add num2, add num3, etc., we are trying to know the next address, what is the next number, and then add it. And we know how many numbers to be added already. So we know that there are n numbers to be added. So it's quite easy to do it as a looping structure instead of writing different add statements for the operations. Okay, so this is the another example of branching, changing the sequence of execution. The control sequence of execution would be changed. Okay, so how would we do that? There is a small theory for that. So let n be the total number of that addition we want to do, and R1 is used as a counter, R0 is used to store the sum, right? This I can explain with your simple C program also. So just let me do this. Suppose how do you write this? You in maybe first year when you studied C programming, you would have written like for I equal to 0, I less than some number n, I plus plus. And if you have an array A of numbers, then you would have written sum equal to, or sum assigned with, sorry, sum assigned with sum plus A of I. Sum plus A of I. So this is what you would have written. So you can just recall this action, right? Where A is an array of elements, I is a count variable, it accesses one by one all the elements indexing into the array, and sum is initially assumed to be 0, and we are initializing it to be 0. Sum is a variable, right? So what happens here in this loop, you can see when I substitute I value, a of 0 will come. Initially sum is 0. So I will take a of 0, the first element of the array, and I will add it to that initial sum and store it back into that variable sum only. Let us say this is my array. Okay, so I have these numbers, say 15, say 20, 25, some numbers I want to add like this, 30. These are the numbers to add. So I'll take the first number and add. So result is 15. That will be stored in the variable sum itself, partial result. Then I go do I plus plus. That means I increment the counter and I go to the next location, next indexing. I equal to 1. So it's a of 1. But now sum is already 15. So you get 15 plus a of 1, right? 15 plus a of 1. I'm trying to show here only. Whereas a of 1 is 20. So 15 plus 20 is 35. Again, 35 gets stored in sum. How long you do it? As long as all the numbers are not added. That is, n is your, so the length of the array are total numbers to be added. So you go on incrementing the indexing from 0 up to you reach n minus 1. Then you have put all the numbers. That till that time, the instruction sequencing is inside this one. That is, the control is not transferred out of the for loop, right? This is what you studied in Zig programming class, to write a looping structure. The same for loop I can also write in this way, because I know that how many numbers to be added. So just see here, I'm just putting it in a reverse way now. Suppose I can write for I equal to n, okay, and I greater than 0, I minus minus, and sum equal to, sum assigned with sum plus a of I. This is also same operation, except that instead of the first number, I'm starting from the last number. Okay, that's how this changes. So I know the maximum number and I go on decrementing that. So that is, I go to the last of the array, then previous number, then previous number, then previous number, then previous number. So I go in this way, downward direction, in fact. So indexing in the reverse direction. Still I do the same operation. And this is the preferred one in assembly language. We use this notation or this kind of a down counting operation. That means we load the initial value as the maximum number. Then after each iteration or each passing, that is after each addition, we try to decrement and see whether we have completed all the numbers. When we reach 0, it means we have completed all the numbers. That is, there are n numbers. After one addition, there will be n minus 1 numbers remaining. After two additions, n minus 2 numbers are remaining. When 0 numbers are remaining, means all are over. So this method we are trying to do in this program. Okay, so what we are doing is that. So you can see here in the program also, I'll show you again. So see, your original number is in R1, sorry, the set of numbers is in R1. Okay. And the set of numbers is in R1, and R0 is like sum, that is to store the result. Okay, let us say this is the result. And R1 has n, which is the total number of numbers. Okay, so R0 is your partial sum, and finally it will be having the full sum after all the operations is over. So initially R0 is 0, like sum equal to 0 is showed there. And then you repeat this so many times. You have to determine the next address and then do this. That's all is your operation now. Okay. So how actually we do in assembly languages, we use this instruction. Because R1 is initially 1, we add the first numbers to the initial result, which is 0. Then we decrement R1, register R1, because after n numbers, in one number is added, then you will be left with n minus 1 numbers. So we just check this. This is the new instruction we are going to see here, branch. So branch means jump to that particular address or location based on the condition over here. Okay. So if all the numbers are not yet added, you will go back and repeat the same addition process. If all the numbers are added, then this condition fails, and then you'll come to the next instruction outside the loop. So as long as the condition is true, you are inside the loop. Okay, that is what is being done here. So this is this operation. So R1 will be decremented by 1 in every pass, and as long as R1 is greater than 0, you will be doing the addition operations. Okay. The special instruction what we are seeing here is now the branch greater than 0. So this is a new kind of a mnemonic what we are trying to do. So it's a conditional branch instruction. Okay. So it causes a change in the straight line sequencing of the program. That means one by one, it is not executed until the condition is true, something is executed. When the condition falls, something else will be executed. So we are altering the sequence of the execution. Okay, this is called as branching, okay, or decision making. Yeah, then when, of course, this is a general example, of course, and you will write these kind of programs in the second module as well. All these kind of programs, writing, adding in numbers or multiplying matrices or addition of matrices, all such programs you can write in the assembly language. All the details will be discussed in module 2. Now, another important topic in this session would be condition codes. So this again, let us come to that examples of arithmetic. We did addition and subtraction of numbers, as we know, right? So, for example, let us say I'm just trying to add, say, these two numbers with, say, one more number. Okay, let us say. So 0 plus this addition. I'm simply taking some unsigned numbers just for you to understand. 0 and 1 plus 1 is 2 actually. 2 we cannot represent. So there's a 0 and a carry, right? So this carry is a condition. That means when I added these two numbers, I generated a carry. Got it? Or we had that error condition called as overflow, if you remember previous sessions. So that means there are certain arithmetic operations which may generate some extra things when operating. Okay, so those kinds of things can be used to take a decision for branching also. Okay, those are called as condition codes. Okay, so that means this carry or overflow or anything like that are stored in special flip-flops called as flags. Flip-flops you will be studying in DSD subject. So for the thing, flags. Okay, so these are the things which we are going to discuss. So condition code register, or it's also called as status register, that is group of such flags which give some information about certain operations like arithmetic operations. The result of that giving some information is called as a condition code register or status register or processor status word, something. Okay, so whenever some arithmetic or logic operation is taking place, the corresponding flags are affected. Okay, that means you may generate a carry, you may generate a borrow, you may generate an overflow, something like that. So 4 commonly used flags. What are the 4 commonly used flags? N flag, which is called as negative flag. So this flag is like a set reset condition, like a true false. If it is 1, it indicates something. If it is 0, it indicates something else. Okay, so a flip-flop is a binary device which can store a 1 or a 0. So 1 indicates certain condition, 0 indicates the opposite condition. So negative flag, what is negative flag? This flag will be set to 1 if the result is negative, else it's clear to 0. Similarly, overflow, we have seen that it is set to 1 if overflow occurs, otherwise it is set to 0. So like that, there will be a lot of such condition codes in any processor what we study in higher semesters also. And these flags will be very useful for taking a decision. Okay, for example, here, as soon as there is a carry generated, I may stop my addition. Okay, because it's outside my system representation format, right? So I can do a lot of such for our other way. For example, I try to subtract say 7 from 5. Unsigned numbers, just for that I'm taking 7 from 5. We know that result is -2. So I can just check this negative sign and say the first number is smaller than the second number. So I can compare two numbers, right? I can compare, like if A less than B, what you write in your C program, if A less than B, if A greater than B, something. All these are actually internally done through these flags only. So A greater than B, A less than B are actually subtraction operations, comparison. After subtraction, when the result is negative, the negative flag will be set. So I know that the first number is smaller than the second number. So a lot of such conditions can be checked using these flags. So to make the conditional branching operation, this would be very useful. And of course, there is another kind of branching called as unconditional branching also. That means without the use of flags also, we can do that. Okay, that and all, when you go ahead to the next modules, we'll try to study all those things. Okay. Now this is how your internal structure looks like for a flag. So you know, that of course, this is a processor. This entire thing is the ALU of the processor. So ALU normally will take two operands, let us say A and B. Suppose you are trying to add two numbers or do some operation on this, and we know that this flag, this is what I said earlier, overflow can be detected basically using the carry out of MSB and carry into the MSB, so using exclusive or I said no. So this is this operation, right? So you can detect that overflow has occurred due to this. Or depending on the sign of the result, you can say the result is negative or result is positive. Like that, there are a lot of things which can be done inside the hardware. And of course, the hardware is already pre-designed. Any microprocessor or any processor you are using in your laptop or desktop has already got this hardware features. And the flags are also predefined. They are already there. We have to just understand how it is working. That's all. Okay. Usually programmer is not allowed to define any new flags because architecture has to be changed for that. So once the hardware is designed, specifically all those flags will be used by us. It can be used by us. Okay. So we can check the condition and all, but we cannot design a new ALU or something like that. Okay. With the existing architecture. Okay. So this is the topic which we wanted to discuss in this session about condition codes, branching, and other related topics. So these are the questions for you just to understand the topics here over here. And we'll go to the next session for floating point numbers. Okay, thank you.